Setting the bar high.
He said he hopes all the slides are like that.
No, I'm sorry. The other ones have more equations.
On the next slide, I have crashed PowerPoint's equation editor.
Yeah, you can see it. Okay, but yeah, anyway. So today I'm just gonna continue the session that we had last week about Gaussian process regression. So I'm just gonna do a very quick reminder of some basic concepts, because then I'm gonna talk about this exact GPs and approximate GPs. So this is quite a bit more important for when we're doing, like, practically we are training these models in Python. And in terms of approximate GPs, I'll talk a little bit about some concepts that are important, such as induction points, and some of the objective or loss functions that are used for these. And then I'm just going to give a very brief overview in GPyTorch how we can define these exact or approximate GPs and train them. And then lastly, I'll just show a slide where I tried with my own data set these three different models, so exact GPs and approximate GPs, and approximate GPs with these different loss functions, so we can kind of see how their predictions are a little bit different. Okay, so just as a reminder again, we have this Gaussian process regression, which is a Bayesian non-parametric method for regression, and in which, instead of us assuming this fixed form for this function f of x, we place a distribution over possible functions. And so here it just means that this function f of x is drawn from a Gaussian process, which can be defined by a mean and a covariance function, or a kernel. And this kernel encodes how correlated our function values are at different points. And here as well, I just have this little example of one of the most used kernels, which is the Gaussian kernel, or RBF kernel, which just in a very intuitive form just says that points that are closer in the input space are more strongly correlated. So then, to fit GP2 data, what we actually want is to learn these kernel hyperparameters. So this is, in this case, length scale, variance, and the noise. And we optimize them by maximizing this marginal log likelihood, MML, of our observed outputs. Oh, yeah.
We don't know how to point
here. Okay. I thought it was showing there as well. So yeah, so we want to optimize this marginal log likelihood of our observed input y, which just aims basically to balance the fit of the data with the model complexity. And so to summarize, this GPR works by starting with here a prior over functions, and it just then conditions it on our observed data to form what we call this posterior, and learns the kernel hyperparameters by maximizing this marginal likelihood. So for regression tasks, the GPR is able to give us this predicted mean function and an associated uncertainty around that prediction. So in practical terms, however, this can be quite challenging to train exact GPs because of computational costs. So usually this exact GP works quite well if we have a small number of data points. But once we have approximately over 1,000 points, then it becomes quite computational expensive in time and memory. And so this marginal log likelihood that we want to maximize becomes untractable. So that's why approximate GPs, or they're also called sparse GPs, appear. And so, so since this marginal log likelihood is not tractable, we need to apply different strategies to try and make it tractable, so we can actually learn an approximate posterior. So the main strategy usually is to use what we call inducing points, which is just a smaller set of points to try and approximate this full GP. I'm going to talk a little bit better about inducing points in the next slide, so I'm just trying to give an overall view of what approximate GP uses. And as well, we need to introduce this variational distribution, this Q of, you can see this Q of U, which is just basically an approximation of the true posterior and is computed over the inducing variable, so our points, our inducing points, so not the full data set that we have. And finally, then there are several ways that we can optimize this. So we can either optimize what we call a lower bound on the marginal likelihood. So that's what you can see here. Let me just take this away. So that's what you see here. Or we can directly optimize this predictive distribution. And for this, we call it predictive log likelihood. So I'll also talk a bit more in detail about these two types of objective functions a bit later. So I'll start just by talking about these inducing points methods and estimating this GP posterior using these instead of our full data set. So as I've mentioned before, these inducing points are just basically a small set of our representative inputs. They're sometimes also called pseudo inputs. And practically, we can either choose them or also learn them during GP training. So if we choose them, they are typically either a subset of our training points, or they are a grid, an input space. Or then if we want to actually learn them during the GP training, we just treat them as these free parameters, and then we optimize them along with the kernel hyperparameters. So now if we look at this here, GP full prior over the training values and the inducing values U, we can write this joint prior distribution with these covariance blocks. So this is just the covariance among training points, this Q of FF, and the covariance among inducing points, and finally the cross covariance between the training and the inducing points. So I skipped a little bit of math here, but basically we can, from these properties of joint Gaussians, we can write this conditional distribution of F given our inducing variables as this, where we have this mean term and this reduced covariance. So in summary, this just means that once we know our inducing points, the function values at all the training points F can be predicted using this mean term and this reduced covariance. So we can say that basically the inducing points just act as a low rank representation of the full covariance matrix. So instead of using the full Q of FF, we approximated it, and we don't need to invert the kernel matrix, which has a size of n by n, which is would be our full training points. We just need to invert one that has size m of m, where m is just the number of inducing points that we chose, which is typically much smaller than our full n. So that's the overall intuition behind these inducing points. They just make it, they act as this lower rank representation, so we don't need to actually work with our full data points. It's just that the data points are correlated with our inducing points, which is a smaller set of them. So now I'm going to talk as well about the different objective functions that we can have when we use approximate GPs. And I will start with this variational elbow. So as I was mentioning before, when we have approximate GPs, we don't compute the marginal log likelihood directly, since it's just basically intractable. And so we need to introduce these inducing points and build a variational distribution, which is the Q of U, and derive a tractable lower bound of the marginal log likelihood. So this derivation of the lower bound is just represented here. And so like in a short summary, it just comes from this, where if we apply this Jensen equality, so this is just our approximate marginal likelihood. And by applying this Jensen's inequality, it becomes this. So really from here, we can get this formula for what we call the evidence lower bound, which is just elbow. And it has these what we call two fixed terms. So the first term is what they call data fit term, and the second one is basically just a regularizer. So this data fit term just encourages the approximate posterior to explain our observed data, while the second term, which is the regularizer, is just the KL divergence penalty. So it just keeps this variational distribution close to our GP prior. So it's mainly used as well to control overfitting of our model. And on the right side, I've also just included in GPyTorch what they describe as their elbow function is basically equivalent. They just as well add this beta factor here, so we can control our regularizer, just a weight on this penalty. And so I think the only thing that I also kind of wanted to note is what they kind of mention here, is that we can see that this elbow formula can also be written as this. So, and if we look at this term here inside, so this is the data fit term, we can see that this observation, sigma observation, so the observation noise is used here in the likelihood, and then is used here in the likelihood, and then is penalized separately. It penalizes the actual variance of the model separately here, since it's divided by the observational noise. So practically what this does is, when we are fitting our GP, the observation noise usually dominates instead of the actual variance that comes from the model. So you can just see here what kind of model this is just the example they have in GPyTorch, but you can see here how it fits the data. So you can see that this uncertainty isn't very well calibrated. So it's mainly constant along the x. So this is usually not what we kind of want to get. And to try to address this problem, another objective function was introduced, which is the predictive log likelihood that I'm going to talk about now. So this objective function is different in the sense that it focuses on this predictive accuracy rather than just maximizing a lower bound of the marginal log likelihood as ELBO does. So rather than treat the posterior approximation as the central objective, it just directly targets this predictive distribution used at test time. And this ultimately results in that better calibrated uncertainty of the model, as you can see in the example as well that I have here. So in this case, you can see that the observation noise is not going to dominate as much as when we use ELBO. So as well here, I just put up this term so we can see how it differentiates from ELBO. So you can see that now this observation noise and the variance of the model are quite different in this term. So they are penalized different. So they call this in ELBO sort of an asymmetry when they are penalizing the observation noise and the model variance. So in practice, the difference here with the predictive log likelihood is that this log is outside this expectation, but this results actually in quite different uncertainties when we apply it to our GP. So now I'm just going to show a little bit of some GPyTorch code and how we can define GPs using this package. So overall, this is the schematic of what we need to define to construct this full GP model. So we need an actual GP model where it can be either an exact GP or approximate GP. We need to define the likelihood as well. And just as a note, usually discussion likelihood just assumes homoscedastic noise, just meaning that the observation noise will not vary along our x. And we define as well a mean, which is our prior. And usually they say that constant mean is a good place to start, but this could also be a linear mean, for example, is also quite popular to use. We define a kernel as well, which also usually is RBF kernel, but we can also have an RBF kernel, for example, with a linear one, so we can have different kernels here added to each other. And finally, we define this multivariate normal. So this is just used to represent our multivariate normal distributions. So for an actual piece of code, when we want to create this model class, in this example is just an exact GP. As you can see, we define here the mean. As I said, usually it can be a constant mean and a kernel. And then this will return this multivariate normal with the mean, with our mean that we define in our kernel. And we define as well the likelihood here similarly. And here I'm just showing the same thing, but in this time for an approximate GP, just to say that in this case it has, like, for example, this this parameter here, which basically asks you if you want to learn our inducing points locations or not. So this is where I mentioned before, where we can choose if we want to actually choose our inducing points or if we want to train them during our GP optimization. But then in terms of the rest, is quite similar to an exact GP. We just define our mean, our kernel, and it returns a multivariate normal, and we define our likelihood as well. And then the training loop is also quite similar for both an exact or approximate GP. So we need to define our loss function, which for exact GPs is the marginal log likelihood. And then we just do a training loop, and our model is going to output the multivariate normal, which contains the mean and the covariance matrix. And then we just compute the loss, so it's quite straightforward. For approximate GP, then again, is quite similar, but in this time we usually define either the loss function as g-elbow or predictive log likelihood, and we optimize similarly the kernel hyperparameters, and as well we can optimize these inducing points locations, but isn't optional. And finally, just for evaluating the model, is also quite straightforward for both exact or approximate GPs. We can just define our test set. Here is just, for example, a smaller, like a subset in the input space, and then our observed predictions will be when we pass the model on the test set and the likelihood, and it will give us the probability, the probability distribution of our predicted output values. And to summarize, to conclude the presentation, I also just kind of wanted to show 3 different experiments I've done with my own data sets, where in this case my data is just the volumes of a specific fetal brain region per the gestational ages. And I've trained them similarly, but I've used an exact GP and then approximate GP. And for approximate GP, I used either this elbow objective function or the predictive log likelihood. So as you can see, the exact GP and the approximate GP using elbow give out quite similar predictions. And yeah, as you can see here as well, this is just a graph showing the uncertainties, the weight of the different uncertainties. So this epistemic variance here is supposed to be the actual variance of the model, and the aleatoric variance is our observed noise. So this aleatoric noise clearly dominates in both the exact GP and the approximate GP using elbow. But when we use this predictive log likelihood objective function, it basically penalizes more the observational noise, and actually what dominates is our actual signal, our variance of the signal. And you can see the uncertainty then expands in regions where we aren't as sure of our prediction, and is more tightly in regions where the data basically fits better in our mean. So that's an overall view of this approximate versus exact GPs. There's quite a lot of math involved in both of them, but I hope at least intuitively is a bit easier to kind of visualize what's going on in both of them, and know when to use exact GPs or approximate GPs, and which objective functions are better to use in specific situations.
Those two are supposed to be similar, right?
Yeah, exactly. Because because basically this elbow is just when we have here, when we just here is when we just do this evidence lower bound on the marginal log likelihood. So they're supposed to be quite similar. The one that's more different is when we do predictive log likelihoods. So that's why you can see that both of them suffer from the same sort of problem, that the aleatoric noise dominates when we optimize it. And so that's why our uncertainty looks quite constant throughout the X in both of them.
I have 2 questions. Let's start with the inducing points.
Yeah.
What are the inducing points for you in your example?
Oh, you mean here?
Yeah.
when I do here.
Yeah.
So for this, I was just trying to train them. Oh, it's not what I want.
And how many of them is there? Is it just
yeah.
some from the
So
training data?
so that's the thing. Usually, practically, you always need to, even if you learn their location, you still need to set them to some number. So the real thing here that I still want to kind of try to understand is how many inducing points is a good number to set.
I mean, in your case, could you use all of them as inducing points?
So that's what I was doing as well.
I guess these inducing points are for calculation of these whatever probabilities, which I didn't really get exactly what they are. But
so that's what I was doing actually. So even because in my case, I don't really have to set it up to something smaller because the quantity of data that I have is like around 600. So it's not like I exactly need to set inducing points to a very low range.
So you could just say 600 and then it will be using all of them.
Yes, but what I do think is that, then again, I haven't tested this, but from my conversations with Euron very briefly, I guess I can still choose a lower number of inducing points and get a very similar approximation of that prediction.
If they choose them well, I guess it would be similar.
Yeah.
How long does it take to train them?
Not a lot. So for my data, so around 600 data points, I think it takes for 2,000 iterations is like around a minute or a minute and a half. Is not very
but if you think
problematic.
About it, if you're doing an atlas for the whole volume, then it will be per voxel. So maybe that's when it starts being important to get it faster. So we'll need to think about it.
Exactly.
That's